hope you can see it properly. I would like to present to you our REveal project, which is led by Hruzova, and it's a project in cooperation of REcovVEry and LTU. The goal is to use residual resources from forest industry to develop low carbon footprint biodegradable collectors for apatite flotation for beneficiation of the mine tailings. We would like to develop and test the potential of the flotation collector to increase the resource efficient use of mine tailings as a source for phosphorus fertilizers. So far, we isolated lignin from spruce sawdust by organosulfur treatment. The chemically characterized lignin has been used for production of the collector via homogenization of lignin in ethanol water solution. Both nanoparticles and microparticles will be used in the study. So far, our results suggest that substitution of fatty acid collector by lignin increased grade and recovery of phosphate. Upcoming activities and the next steps: laboratory batch flotation tests using the lignin collector will be conducted on mine tailings delivered by REcovVEry. The recovered apatite will be evaluated by its grade and recovery, and the impact of composition of selected mine tailings and processed water on the flotation process and apatite recovery will be addressed. That is it. Thank you very much.
Thank you, Katerina, and it will be very interesting to follow the results from your next steps. So thanks again. Next up is Martina Petranikova from Chalmers University of Technology.
Yes, thank you. Thank you very much. So I will talk about, or I will introduce our project regarding the recovery of lithium from the batteries with thermal pretreatment and just water leaching. So maybe, okay, takes time to shift to.
You can't really shift it?
No.
Maybe you stop share and share again.
Okay.
No rush.
Mm-hmm. So let's see now.
We see it very well.
Yes.
There it went
Third
away.
time is a charm, maybe.
Yeah, third time.
Yes. Can you see it now?
Yes.
Yes. Okay, something is wrong with the shifting. Okay, I will continue talking about. I don't have to show the results, so it's better to talk and then take the time. So why to recover the lithium? Because the demand of lithium is increasing rapidly, and for European Union, lithium is a critical raw material. So we really have limited sources of lithium in European Union. What we can recover it from are the batteries. But nowadays the batteries are recycled using either pyrometallurgy or hydrometallurgy. In the pyrometallurgy, the lithium is rarely recovered, but in hydrometallurgy it is. However, in some steps, lithium is lost. So then it is recovered in the end as the product. So our idea was to recover the lithium after the thermal pretreatment, because this is usually done and used for the batteries recycling, just with the water leaching. What we did, we tested the pyrolysis and incineration, and we tried to see the addition of the graphite, which is already, and carbon, which is already present in the batteries, either in the form of graphite or in the form or the organic components or the separator, which is polypropylene. And if we don't use this additional graphite, we can recover approximately 30% of lithium from the batteries with the water leaching. If we add some graphite, we actually shift the recovery to approximately 60% in both incineration and pyrolysis. And the purity of our product is now 97%. So our further work will be focused on the recycling of or the improvement of the recovery of the lithium, because our goal is to push to 95%, and currently we have achieved 92%. So our further work will be to try to push it really to 95%, not to lose any lithium within the process, and also to purify it. So far, the only impurity which is sort of co-leached with the lithium is aluminium, which is very good. So from all the metals present in the batteries, what we get there as the impurity is only the aluminium, which we will separate from the lithium and thus purify the product to the purity that we can use it for the battery production. So that was my presentation about. I hope I will be able to share it another way. So thank you.
Thanks so much, Martina. I mean, of course, how we can start to recycle in high percentage grades, and of course as well to have it into the ecosystem in a sustainable way is so important nowadays. And I mean, we are not there yet, but maybe 20, 30 or 40 years from now, we will have less need for primary resources and more from what we can recycle. So that kind of work is so important, of course. Thank you very much. We look forward to follow your further results. Cheers. All right, next up will be Mikael Larsson from Swerim.
Yes, so let's share my presentation. Okay, this is a presentation of sulfur removing from sulfur containing iron ores. Project partners are Kaunis Iron and Luleå University of Technology. This is the pre-study that started before summer and is going to end now before the end of this year. So the goal of the project was to suggest a process concept that allows to treat and transform the sulfur containing mineralizations that Kaunis has into a mineable iron ore. We have done some initial studies, and we think that by having a thermal treatment, we're able to remove sulfur as a sulfuric gas, and by that creating a sulfur-free iron ore mineralization that then can be further treated into a pellet or some other type of iron product. The aim is then to increase the knowledge of this process concept and to understand the theoretical mechanism that we need to handle in order to be able to remove the sulfur, as well as understand the favorable process windows regarding temperature and gas composition for this process to happen. So so far we are in the end. We have done some calculations theoretically. Based on these calculations, we can see it's a clear temperature where sulfur will be transformed into a gas phase. This happens somewhere around 550 degrees. If we would be able to do this, we would then be able to treat this material without needing a flotation step. In the initial studies, we have done some small-scale tests, and we have identified two sulfur peaks, one at 500 around, which corresponds to the theoretical calculations, and one at a higher temperature. So we also have done some TD tests, and based on these, we have been able to quantify that before, or the first step, the first peak, contains about 50% of the sulfur. And if we can run this up to, say, 1100 degrees, then almost 100% of the sulfur has been removed. This doesn't really, it's something that is not really clear in this. And one of these things is that we can't understand why this second peak is happening. It needs to be...
Mikael, 1 minute, please.
Yes, it's another species as well as perhaps other compounds that is formed. And this is what's going to happen now in the end of this project. We are going to do repeated tests, and we are going to do further tests with also the flotation sand to see what happens if we treat the sulfur flotation sand from containing high sulfur contents. This will be ended then in the end of this month. So we are in the end stretch of this project, and hopefully we can go further with a full-scale test. Thank you.
Thank you, Mikael. And of course, very interesting. And of course, if you can remove the sulfur from the iron ore, or the product from the iron ore already from the beginning, I mean, it will be a tremendous difference in the impact that we make further down in the products. So thank you very much. The next who will come up here is Charlotte Andersson from Luleå University of Technology. Charlotte, most welcome.
Thank you. Very nice to be here. You can see me and hear me?
We can see and hear you.
Let's see if I can share my screen then. So can you see it?
Yeah, and you put it on the present. Yeah.
What are you seeing now? You're seeing the presentation, the
yes.
right? Yeah. Okay, so I'm here today to talk about this pre-study, role of magnesium in iron oxide pelletizing. It's a joint project between Luleå University of Technology and Kaunis Iron. And I am the project leader. I'm an associate professor at process metallurgy at LTU. So a little bit about the background. Today, magnesium is an element that is needed sort of in the iron and steel making, and it's often added. Magnesium-bearing minerals are often added at some part of the process. And the idea with this project is to investigate if we instead then could use an magnesium-containing iron ore to avoid this step of adding a magnesium-bearing mineral. But it is also known that magnesium might have a negative effect on the properties of pellets. Their mechanical properties, but also their mechanical properties during a reduction. So the purpose of this is then to study the correlation between then the magnesium distribution in an iron ore concentrate. So where is the magnesium present and to what extent it is for two different iron ore concentrates that might have then magnesium in different parts of both in the actual iron ore, but also in gangue. And to understand the theoretical system of magnesium, iron and oxygen, and see what is possible to do theoretically. To apply this knowledge and create pellets then from these two concentrates, and then try to correlate the origin of the magnesium to the pellet quality. So, and results so far is that we have done a thorough characterization to identify what minerals is it that contains magnesium and how does the distribution look like in different particle size fractions. And here you see an example of the mineral liberation analysis that has been done. And we have also done a thorough review of the theoretical phase system and investigated variations then with both with theory as well as with thermodynamic modeling to see the effect on the actual magnetite, so the iron ore and the iron oxide.
Hello.
how it will vary if we vary the magnesium, vary if we vary the magnesium content. So the final step is then to do a more detailed study of the lattice-bound magnesium and do the final pellets with the recipe that's decided, and the final correlation between magnesium origin and pellet properties. And that was all. Thank you very much.
Thank you, Charlotte. And you talked about background, and if we shall talk about background as well, I mean, you used to be the program director for a few years.
Yes, that's why it's so nice to be here on the other side, maybe. It's
the
right term.
So very interesting to see you in this role, and of course a very interesting project. We will hear more from this. We are sure about that. So thanks again. Next out will be Hesham Ahmed from Luleå University of Technology as well. So please welcome.
Yeah, hello. Thank you for being here. It's very interesting and exciting to listen to all these presentations. I will try to share my screen.
Perfect. Then you will now we see it very good.
Okay. Well, the project is transforming mining residues to valuable products, and we call it residue to product. I'm the project leader from Luleå University of Technology, and we have Boliden Mineral as the only partner. And the project started before summer, and it will end either the end of this year or maybe a little bit before. Now you see the next slide, right? Am I there?
Yes.
Okay. Well, I will give a little background about the project. You know, the waste from sulfidic mining of metals like the copper, zinc, and lead, they actually represent the largest volume of waste generated in mining industry in Europe. An important waste generated from this mining of sulfidic ores is the pyrite tailing, which is generated from the flotation process of sulfide minerals. And one of the issues with this pyrite tailing that after exposure to the atmosphere, it forms like what is called as acid mining drainage. And one way to solve this problem is to neutralize it with added alkalis. And today they add calcium oxide or calcium carbonate, but then this leads to the formation of gypsum, as you see here. So we face two big piles of pyrite tailing and gypsum. So the aim of this project is to develop and validate a novel recycling process for simultaneous treatment of gypsum and pyrite residues. And at the same time, the project aims to produce a valuable product such as calcium oxide, sulfur dioxide, and metallic iron through this. Okay, the results so far, we started with some theoretical exploration, and then we found that the pyrite decomposes to pyrrhotite and sulfur. You're muted, Niklas.
Yeah. Sorry, I wasn't talking to you. So continue your great presentation.
Okay, sorry. I thought you were reminding me with the time, but anyway. Well,
now
then
we'll say 1 minute, and now you can continue.
Okay, the pyrrhotite then reacts with carbon and calcium oxide to form metallic iron and calcium sulphide. And then the calcium sulphide can react with the gypsum and form calcium oxide and sulfate in the temperature range of 900 to 1200. So we started the sampling, the pyrite tailing, as you see here, and then the gypsum. And also we tried the pyrite decomposition, which we have done successfully. The upcoming events will be study the possibility of pyrrhotite conversion to metallic iron, and also study the possibility of converting gypsum to calcium oxide and sulfur oxide. And then we end up with an overall evaluation of the product and process step, and then reporting. Yeah, and that's it.
Thanks a lot. And sorry for some reason, Hesham, we make you a bit confused. We had a sort of a Wi-Fi breakdown here for a few seconds.
Okay, no worries.
That's fine. But thanks a lot, and thanks for a very interesting presentation from a very interesting project. So we will hear more from this, and we are looking forward to it. Dragos Dancila, you will be our next presenter.
Yep.
And we are seeing your screen, but not in present.
Yeah,
I'm presentation mode.
Yes, I'm working on that.
Maybe you shall continue as you had. Now it's perfect. Thank you.
Okay, thank you very much for the opportunity to present our works here. It's very nice to be here and see all the great works that are going on around mining in Sweden. So my name is Dragos Dancila. Mining is not really my main research topic, but there is a convergence as we're working with high power microwaves. And we try to introduce new concept using high power microwaves in the mining environment in Sweden. And this project then it's a collaboration between Scandinova, a company here in Uppsala, and Persirock, a spin-off from Uppsala University. And we got also support from REcovVEry to investigate comminution processes using microwaves. So the goal of the project then is to investigate the premises of a very efficient comminution method using extremely short electromagnetic pulses of very high intensity. So this means that we're gonna use electromagnetic fields, so electrical fields, as to induce small cracks in rocks, in ore. This is not a new track. It is existing already. We have, in the state of the art, we have a demonstrator, a pilot demonstrator in the UK, where they achieved a high throughput of 150 tons per hour. And they are using high power microwaves. So there we talk about 100 kilowatt sources, microwave sources, to treat ore. So they induce fracture in rocks, and they are using very low energy to realize that. So we talk about less than a kilowatt hour energy per ton of ore. So the questions of the project we try to answer here is how can we position the Swedish mining industry on this track, and then how can we do that better? So this is a pre-study. So we are investigating what we can do with our technology. So we started looking at the impact of microwaves on different rock samples. And then the way to assess that is to use this method, which is called P-wave velocity test, so that we apply ultrasounds on rock samples. And then we measure the velocity, the sound velocity. So we have samples that are measured like that before treatment with microwaves and thereafter. And we take the ratio between the velocities. So here are our first results. So you see that after exposure with microwaves, low power microwaves, but we still see a decrease in the velocity of the sound in the rock samples. And this,
1 minute.
Yeah, sure. And this is explained by the fact that microwaves induce cracks, and then the sound has. It's a proof that sound is travels much slower after exposure with microwaves. So the upcoming activities is to use klystron, which is a very high microwave power source. So that's that's coming from Scandinava, and then to put in place test setup with that device and to realize very fast, we talk about microseconds, exposure to very high microwaves, and that's to induce cracks in a fraction of microseconds. So that's it. Thank you very much, and I will be happy to answer further questions. Looking for collaborations. Thank you very much.
Thank you very much. Very interesting, and of course, can we have the Swedish mining industry on track? Yeah, that is a great goal, and that is, of course, very important for us to see how we can do it in the best way at this area as well, of course. Next up is Andreas Johansson from Luleå University of Technology, and I see that you have already started to share your screen, and we see it perfectly well, and we see you as well, Andreas. So please welcome.
Okay, thank you. Great. Can you hear me as well?
Yeah, perfectly.
Good. Okay, so I will be talking about a project ECO, efficient comminution operation. So we have also been dealing with comminution here. Really fascinating, actually, to hear about microwave-based crushing from Dragos just recently. Really interesting. We've been dealing with a traditional kind of comminution, I would say, crushers and grinding. So I've been leading the project, and the partners have been, apart from LTU, we had Optimation, a Luleå-based consultant company, and also Innovative Machine Vision, which is in Australia, and of course Vale, a really big Brazilian-based mining company. So the project ended in June this year, so this is sort of a wrap-up of what we did. Very briefly though, since we've been doing this for several years, so there will be not much detail in this presentation. So the overall goal was to improve the efficiency in comminution chains in the presence of changes in ore properties, product demands, wear, and so on. So we want to maximize production, minimize energy, and so on online using, in real time, using available measurements. And in particular, measurements of size distributions, which are now available commercially. So the expected results will be these algorithms that optimize operation continuously by changing variables in the machines. And also to test, implement at Vale. This last point has been a difficulty, of course, since the pandemic has made it impossible to travel to Brazil. So most of the results are in simulation. So these are basically just a few examples of what we've been doing, but overall we have made an effort to put everything we do in a framework of modeling and implementation, so that this can be reused and this framework can be reused in the future for continued efforts on this area. A lot of the efforts have been directed towards the modeling. We need dynamic models of the processes that we want to control. So we've been focusing on models for the energy consumptions in crushing, for example, and other things that were lacking in the literature, like segregation effects in stockpiles, when the large material falls onto the sides and the small material is stuck in between. Compartmentalized ore silos and a lot of things here. And then developing optimization tools, online optimization tools for these. For example, how to draw the optimal size distribution from a stockpile, how to maximize the capacity in a crushing circuit in real time, given changes in ore properties and so on. And also we made some efforts in the measurement technology, the size distribution using 3D laser scanning is really has great potential compared to the ordinary methods where you just use a camera image. With 3D laser scanning, we can achieve much greater accuracy and robustness. This has been hampered with computational load, but we've been able to find algorithms that can do this now, so that we can use this kind of measurement online in real time algorithms. So, as I said, the project is ended, but it feels like we barely only scratched the surface of this area. So one obvious thing is, of course, to seek new project fundings to follow up on all the leads we found. We'll be finishing some publications that we've been working with. We also have a good cooperation with the Vale now. We have a postdoc working here at LTU now who has been at Vale before, and also a guest researcher from Vale. So that's also an important outcome of the project. Okay, so that was all for me. Thank you for listening.
Thank you, Andreas, and very interesting results, and what we see about both how we continue to strengthen our international collaboration, which is of course very important, and as well it will be very interesting to be able to see your publications for people. Will all of those be open for public, or how will it be there?
Yeah, we are aiming for open source journals, yes.
Perfect. And when you have that, of course, you as well as everybody else, you will send in to us in the program office to Therese, so we can as well help you to share those publications. Yeah.
Yes.
And if somebody wondered why Andreas had a few more minutes, this was a full study, and we had the earlier 6 at this theme was pre-studies, so you had a few more minutes, and we are very happy that you could share those results with us, and great work from the whole team in this project, which it seems to be. Thank you. Another full-scale project will be the last presentation for this theme and before lunch. And so we say welcome to Caisa Samuelsson from Luleå University of Technology.
Thank you very much. I hope you can hear me, and I will try to share my screen.
Yes, we can hear you and your beautiful background. Now we see a screen as well.
Yes, and let's see if I can get it in slide mode. I guess so.
Oh.
So thank you. My name is Caisa Samuelsson, professor in process metallurgy at Luleå University of Technology. And I'm also the project leader for this project on processing of copper concentrates. And our partners are Boliden Mineral, both the mine site and the smelter site. And the developer of measurement technology is Semtech Metallurgy. And we have just gotten an approval of extension, so we will continue the full year next year. And the aim of this project is to increase the flexibility in the selection of raw materials and selection of concentrate, and this by optimized roasting. And roasting is a process that can be applied on this kind of concentrates prior to smelting to remove some of the minor elements as arsenic, antimony through vaporization. The roasting is is dependent on the properties of the concentrate, such as the mineral composition and also the different minerals that are in the concentrate and how they react with each other. So the project is consisting of several parts that are linked together. We have done or are still doing partly testing in lab scale furnaces, combined with an in-depth characterization of the material before and after the roasting process. And we are combining this with process modeling, which is based on thermodynamics. And we have looked at the thermodynamic data for arsenic and antimony, as there is a lack of data for those, so that is why it's a little bit specific. And this is also validated with available process data and also with the results from the lab scale test. And full scale tests are done to test these materials in full scale and also validate both the lab scale test and the process modeling. And also we have this online measurement technique, and one should say that measuring online in these kind of conditions is quite difficult. It's not straightforward. So what we have done so far is to find a suitable sampling point where we can install this measurement technology. And the upcoming activities, we will continue to do sampling campaigns and also discussing further full-scale tests. Installation and testing of the measurement technique is hopefully done by the end of this month. And we will also focus next year to evaluate the results and also on the process modeling. And there will be a presentation of a PhD thesis during the first quarter of next year and reporting. So that was a very quick and short presentation. Thank you.
Thank you, Caisa.